Okay, voice is connected, and let's see if I can get my video connected. There we go. All right, I think I'm up and running. Let me know if I'm not. Ooh, should be live. Okay, for those of you watching on Twitch, occasionally you will hear me typing frantically, which is basically me over on Discord doing stuff. And hopefully we'll have some people joining on Discord momentarily, so that I don't just start talking to the air. Um, all right, let's see. All right, people joining. That's good. That's good. Welcome, welcome, welcome. All right. Um, it looks like I got the vast majority of the projects in. 99, 95%. I'm not sure, something like that. Working out a few things. If you got an email from me, or you may have gotten an email from me, one or two people, about just making sure that you have submitted both on LMS and pushed things. Um, Anthony, if you could mute your microphone for the moment. It sounds like you keep kind of cutting in once in a while. Unless you have a question. If you do have a question, jump right in. But we'll try to keep things fresh here, fresh and clean. So, okay, a couple of you may have gotten an email from me. I'm not sure if we had anyone kind of who signed up for the course and then decided not to be in the course, but just like to make sure. But it looks like we're in pretty good shape. We'll work things out. I know we kind of push things as quickly as possible. We're online. Lots of things have changed, so we'll work it out. You know, if we're off to I think we're off to a pretty good start. Maybe slightly rocky. No, not rocky, but actually better than usual. Pardon me for I'm riffing while waiting for more people to come to the class. So that's what I tend to do. All right, so project one is sort of behind us. The goal of project one is really, it wasn't to be the best game in the world, obviously. It was really more to kind of just get some basic concepts down, become a little bit more familiar with, of course, the Unity IDE, the integrated development environment, the idea of Unity objects and components, some of the ways that they, of course, hook over to the C# side of things, how we can invoke scripts and methods inside of classes from the Unity IDE, buttons and events and so on. And obviously to also be able to sort of manipulate components on objects directly from scripts. We covered a lot of territory. It's only been 2.5 weeks, and we definitely covered a lot of territory, so thank you all for kind of hanging in there. It was a lot. We also obviously learned a lot about C# along the way. We learned the basics of data types, declaring variables, initializing them, a little bit about classes in general, a little bit about scope in terms of public, private, static, so on. A little bit. We'll kind of get into more of that as we go. And what else? Let's see. Yeah, we learned quite a bit, and structural kind of program flow and structure, things like if and else, and of course for, do, while, for each, and so on. Lists and arrays. Covered a lot of territory. So I think I'm very optimistic. I think we're doing well. As far as the projects go, I haven't looked at all of them yet. I hope to have them all set, graded, things up by Monday. So I'm going to try to take my time over that. Usually I'm kind of flooded with these. I'm happy to only have around 20 this time instead of my usual somewhere 50 or 60 of them to work through. So as you can imagine, that's why I like to keep them sort of straightforward, so I can focus on the programming piece of things and not necessarily on finding every last key in every last room and every last trap and pit and poisonous spikes and all that kind of stuff. So leave that for things as they get more elaborate. So let's talk about vectors in physics, and also the key topic here, letting the engine be an engine. All right, some of the things that we did in the past project, let's see, we'll switch over here. In this project that we just finished, we kind of did a lot of things by brute force. In terms of comparing distances, moving the player around was a little bit of a brute force kind of thing. Some of what we would normally do with kind of collisions and objects and physics and things, a lot of that could be handled sort of certainly sort of more automatically by the engine. But it's to give you then an appreciation for them once you get all these functions sort of built in. So makes life, so you can sort of understand a little bit about what's under the covers. That was the idea. So I should get those back to you, or at least the my feedback on that to you sometime by Monday or before class on Monday. If you do have any questions about them, last minute, if you do have some changes, if you suddenly had an aha moment and wanted to add something, the nice thing about Unity Teams is that you can sort of add things as you go, but I'm going to try to compare everything based on the version that was submitted last night. The other nice thing about Unity Teams is as you submit things, I can track when they were submitted, when things changed and all that. So that works out really, really well as well. Okay. So for those who haven't already checked, there is there's this morning and last night I posted some more videos that are useful for this week's topics specifically. Things like starting to move some assets into projects. Also, we want to kind of resolve the whole how we're going to put all 4 scenes, our single room adventure, our apple picker, our kind of top-down shooter, and our platforming side scroller into one project. So we're obviously going to need to do that a little bit more. So work on scenes and kind of get that all kind of squared away. We'll focus on that a little bit. And part of that is going to be kind of managing assets across projects and bringing things in. There's a little video about that. And there's also a video about creating prefabs, using Instantiate to create those prefabs, and then using arrays and lists to manage those collections of prefabs. Okay, so definitely go back and see the couple of videos that I posted. They're all part on the YouTube playlist. I posted the YouTube playlist also in the lecture notes. So double check on that. It's posted all over the place. Anyway, so there's a bunch of other, probably an hour's worth of videos. So I'll try to keep this, let's see, if I can keep this to around an hour, that would be great as well. I don't want to give you, more than 4 hours of stuff to digest every week if you don't have to. So back to the topic. All right, hopefully we've probably got as many people as we're going to get for the day. So thank you very much to the 2, 4, 6, 8 of you that are here. Just so you know, one of the things I'm going to now do from now on is I am going to screen grab the attendance off of there. So people should be aware that, yes, I am going to kind of keep track of that. So it's kind of, I want to see who's paying attention and whatnot. So this will be important. All right, vectors in physics. Let the engine be an engine. Let the engine do the hard work. We should focus on the creative side of things, but let's let the engine do its thing. So before we entirely do that, we need to know a little bit more about some math. Okay, we're not going to get really, really crazy into linear algebra, but we're going to touch on it just a little bit so we can kind of understand and appreciate a little bit of what's going on in the physics engine and so on. So we're going to touch on some of that briefly as well, especially as we start introducing physics and scripted motion into our games and how they kind of work together and how they sometimes fight one another. All right. So let's see here. Let me see if I can. All right. So let's first, if we want to understand vectors and physics, certainly first have to understand numbers, right? And you might say, well, hopefully this time around, since you're more all upperclassmen, I'm sort of preaching to the choir, and these are things that you've already gone through. So pardon me if it is a little bit of review, but maybe it'll kind of put things in a different light than you're used to, maybe. So a number is the way we measure things, right? We have some quantity, the amount of something, a quantity or a magnitude. It's easy. It has one dimension. We just have some number. It tells us one thing about it, right? If you want to know how far apart 2 points are, for example, which is a useful thing, like distance, right? The distance, we use that in our little adventure game. We calculate the magnitude of the distance between those points. Okay, that's what's going on in the distance function. It's calculating the magnitude of that distance. That's why we compare 2 points, we come up with a single number, right? It's just the distance between them. That's representing the distance as a number, right? However, often you want to know more than just that distance, right? You want to know things like, okay, what direction was that in? What's the relationship of those 2 points? Just having a magnitude, just having a distance is just not quite enough, right? So often we want more information. We want to know, where is the second point relative to the first? Is it sort of in front of it? Is it behind it? Are they aligned with one another? And those get even more elaborate. There's a little bit more. You have to get into orientation and so on. But in order to work with all those, we need more information than just the magnitude between things. We need some sort of indication as to the direction, right? And for directions, now this is where vectors can be vectors. We've used vectors, and in a lot of cases, we've just used vectors to represent a position, an x and a y. Right? In our games so far, even though we were using vector 2, maybe vector 3, depending on how you're doing things, for the most part, you really just use those as a representation of a point in space, an x, a y, and perhaps a z. Okay. So somebody's got their microphone still on. So double check that just in case. Xiaolong, I think you have. Okay, great. We're in good shape now. All right. So the funny thing about it is, of course, okay, I should mention this. Okay, so this is how we resolve the fact that we sort of use positions as if they were vectors. So what a position is, think of it this way, it's a particular type of vector where it is measuring the direction and distance from some origin or from the origin away from 0, 0. So if you think of all vectors in terms of that, even if they're a position, right? So if you have a position of a single, a position of a point is its distance and angle from the origin, right? So even a position in and of itself, if it wasn't positioned in relative to something else, it really wouldn't be a position. It would just be a meaningless point in space that had no frame of reference, right? So really a position is a vector measuring direction and distance from a specific origin, right? That blows my mind just even thinking about that. All right. So it is a measurement of a quantity from some specific position, right? So we can use this same notation for points and vectors. Just kind of be careful. Keep that in mind, right? Remember that kind of relationship, what we're talking about. So we kind of interchangeably use them, but it can be, time to time, remember, just keep that in mind. So we use vectors to describe all sorts of quantities in the 3D engine. So for example, we have velocity. So the speed of an object, normally the speed in a certain direction, right? We don't just say 50 miles per hour. We would say 50 miles per hour in a certain direction, moving in a certain, a certain rate in a certain direction at a certain, and so on. Force also has that. So you have a force with a direction. And in our case, we have some offset from another vector quite often, or another position. Right? So often a vector is what points from one position to another position, whether that position is the origin or that offset might be from another vector. And that's what's telling us that relationship between those 2 points. Again, in our simple game, it was just, we were able to just use the distance. We said, okay, I am warmer because the distance got smaller. I could give the player that sort of hint. And we certainly could have done things that were more elaborate by saying, okay, the x decreased or the y increased, and say, okay, we're getting closer, but it's up and to the left or down and to the right sort of thing, right? We were closer and we hear some direction. Could have done that. Maybe we'll do that in the future. So this is weird. Why is it asking me to activate Windows? Odd. Very odd day today. All right, so continued. So if we want to combine vectors, we can certainly do that. Again, if you've taken any linear algebra, you've probably done these sorts of things. So if you want to move a certain distance, you want to follow a treasure map, you can combine vectors. 5 paces north, 6 paces south, 4 paces northeast, and you keep adding these vectors to combine them to one another. Right? So your ultimate location is the combination of all the vectors that you have moved through. You moved so on and so on. You may actually move in a kind of crazy wandering path, but ultimately it gets you to a specific point or some new location. You can do the same thing with forces, the same thing with velocities. So an object can have multiple forces acting on it, and you may try to move it according to certain velocities, right? You can actually combine all those things simply as well. However, positions cannot be combined. Right? An absolute position cannot be combined because each one assumes the same origin. It's not a distance between them. So you'd be combining them to the same. So what would that even mean? We don't know. So you can't add positions. That's in being strict about our terminology. So we typically add vectors to find out where we end up as an offset from a position, like I mentioned, our example of, following a treasure map, kind of move this way, then that way, then this way, then that way, we wind up in a new position. But we can't add positions, but we can subtract them. This is the interesting part. By subtracting positions, we basically say, okay, how did I get here from the other position? Right? So that's kind of the paradox, I suppose. We can subtract them to get their position or their offset between them, but adding them really does not have a valid use, a validity of its own. All right. So let's come out of the dark, look at the light here a little bit. So what are vectors? Let's talk about them in general. How can we think about them as a data structure? So they are basically a direction and a magnitude, right? A direction and a magnitude. We normally don't represent them that way. We kind of represent them as some offset or some combination of those two, right? We don't say, the overall direction is this and the overall magnitude is that. We say, well, okay, here's the x component and the y component, or the x and y and z component, which give us that direction, and we can mathematically come up with a magnitude from there. But most of the time, we're going to be thinking of these vectors in terms of their individual components, two-dimensional or three-dimensional components, which is why they often do sound a bit like a point, right? Because we're thinking of them in terms of the coordinate system as opposed to their pure form, their direction, and their magnitude. Right? So it's kind of an interesting thing. Now, eventually, if you continue on in 3D math and geometry and game architectures and so on, you'll learn about kind of the way that we represent rotations in terms of vectors and magnitude, and that's a much more complex topic, but it becomes important, very important at that point. So keep this in the back of your head for now. Right. So some of these things we'll be able to more immediately use them. In other cases, it'll become more obvious, hopefully, in the long run for you. All right. So just by way of review, this is I'm hoping I'm preaching to the choir here. Simple case. We have 2 points. We have a point A, which is at 2, 8. Right. It's offset 2 in this direction and 8 in this direction, and B, which is offset 5 in this direction and 3 in this direction. Right. Simple enough. In order to figure out the vector that is in between them, we can subtract the two. So we get the distance. We say, okay, if we subtract 3 from this one, we subtract 3 from 5, we get 2. And if we add this, we add -3, that, and we add, I keep going on we add 5 to this 3, we get 8. Right? So this isn't a subtraction. This is an addition of a negative number here. Sorry about that. I get going on my... So that's the simple way, right? So this is this vector. And if we looked just at the vector in and of itself without the reference point of either of those points, we can see that, yes, the vector itself represents this number and offset from the origin, right? So it's important. The vector it points to the first term of the subtraction, right? So that's why we can add this to this term and get back to the one we were at, because it is a subtraction of A from B, or sorry, the other way around. Yeah. Okay. Now, thankfully, for the most part, we don't have to worry about really doing operations on individual components of vectors that much. You probably did it a little bit in your game in terms of when we wanted to move north. You probably added specifically something to the y component, or maybe you added a vector that only had 1 in the y component and 0 in the other two components, right? But typically you were working with vectors and you were using their components, but then the engine itself or the library itself, they were handling sort of the combination to make sure everything wound up hopefully in the right spots for you. All right. So more and more we'll rely on built-in functions to do these sorts of things. That's the reason we use classes like vectors, so that we can have those built-in functions to deal with that. So, for example, here, if we wanted to determine the length or magnitude, similar to the distance, we wanted to figure out the magnitude of a vector in and of itself, you can ask that vector for its magnitude. Right? Offset.magnitude will give you the length of that vector. So this, jump back here, we saw this length of the vector, its magnitude. Unity and its math libraries will give that directly to you. So if you have a vector, you could just say vector name dot magnitude. It'll do the right thing. It has a built-in variable that will allow you to get that directly. So you can go ahead and try that. If you wanted to go, if we had our C# simulator, we could go back up and do that sort of thing. I'll leave that for you to try. Right? And the way it's figuring that out, of course, is just using the Pythagorean theorem. It's easy enough. It's just a right triangle, right? We're working with a right coordinate system, x and y, where they are orthogonal to one another. So it's easy enough to figure out what the magnitude is. And it does it for us. It's nice. It's convenient. Okay. So why is this important? Why do we talk about it in terms of game development? Well, a lot of the time, what we now are typically doing, and what we're going to talk about a lot in this class and so on, is games as sort of a simulation. So we're not talking about necessarily doing chess or Go or kind of board games. Although if we're doing a simulation, a physical simulation of those games, we would deal with the real geometry that they'd have. But for the most part, we are going to talk about things in terms of their physical representations, their movement, their positions, and so on. And that becomes important. That's why we really kind of stress this sort of, this combination of physics vectors and the way they work together in game engines and in game programming. Right? Quite often, you're going to want to manipulate vectors. You want to change the magnitude. Why would you change the magnitude? Well, changing the magnitude is an increase in speed, potentially. If you're using a magnitude to represent the current velocity of an object and you want to change it, well, you have to add something to the speed, perhaps because you want a speed boost, or you want to apply drag. You want to slow something down because it hit a sticky surface. That's all going to be a change in the magnitude of the velocity of the object, right? You can do things like stretching, scaling. So if you want to make something larger or smaller according to a factor, you can multiply it by some number, right? When I say multiply a vector by a number, that's multiplying a vector, a multidimensional structure, by a single scalar, right? So if I scale a vector, I want to cut it in half, say, I would just multiply every element of that vector by whatever the scalar is, right? So when you're multiplying a scalar by a vector, it's a very simple operation to just take the scalar and spread it across that whole number, right? So you can do things like say, okay, here's my offset vector, and I can multiply it by 2, and that's going to increase the magnitude by 2. Okay, so it's increasing the magnitude. Let's see, did I just misspeak? No. All right, we'll think about that. Sometimes I get going and then I plays in my head in different ways. All right, so if we want to increase the speed of something, we want to double the speed of something, we can double its magnitude. All right. Now, sometimes you want to set the speed of something. Imagine setting it to a particular speed. In that case, you might want to set the magnitude. So it's currently going in a certain direction, but you want to change the speed without changing the direction. That's kind of tricky. So you want to maintain the speed, or excuse me, maintain the direction, but change the speed. And this is for the first time we get into this case. We want to work with the direction. We want to use the direction without regard for the magnitude. So now we're kind of getting into the situation where, okay, sometimes we just want the magnitude, sometimes we just want the direction, right? And in order to get that direction, we do something called normalization, or normalizing the vector, right? We're basically saying, okay, take the vector and divide it by its magnitude, which that is going to give the vector, it's going to turn the vector into the same vector but a length of 1. Or it's not the same vector, it's going to have the same direction but a length of 1. Right? So sometimes if you have a vector and you only care about its direction, this is the shorthand version. If you have a vector and you only care about its direction, you can use this offset dot normalized to normalize that vector, give it a length of 1. So if I wanted to point something, want to let it keep going in the same direction, but have a velocity of 2 in that direction, I would use the normalized version of that vector and multiply it by 2. Right? It's a little bit tricky. You have to, as we try things out, they'll make some more sense. All right. So a few vectors worth mentioning. Unit vectors represent the kind of cardinal directions, or they represent. They're going to be a direction, a pure direction that has a length of 1. So those are going to be unit vectors. And non-unit vectors you're going to use for forces, velocities, and so on. They're going to have some sort of different magnitude depending on their forces and so on, right? So normally, they're not the cardinal ones. I don't know why I said that. Unit vectors, often you use the cardinal ones that are units to kind of figure things out. But basically, unit vectors represent only the direction. They only have a length or magnitude of 1. So, okay. Whew. That was a whole bunch of things about the origin of vectors. So let's this is gonna be a little bit more math. Now, let me pause for a second, and I'm going to ask a question over in the Discord chat about how many of you have taken some sort of linear algebra and already know all this stuff. All right, so you can respond to that. Feel free, and if you don't worry too much. It's not going to really get in the way, okay? This is more like, some of the stuff you could just say, okay, let me sort of remember what he was talking about. Let me matrix transformations, okay. Vectors pointing in directions, okay. Just think of them as concepts. I'm not going to ask you to write out this as code, okay? So it's more, some of this is going to be informational, but it will certainly help you with regards to debugging things if you have a more of an understanding for the math underneath, right? And what I'll do, I thought I had one handy over here. Yeah, okay. For this next section, if this next section really hits you as sort of like being very out of left field, I'm going to point you at a PDF file over here. It's over in the Discord, which is a review of sort of transformation, about how to use mathematical transformations with matrices and vectors, and it'll give you a little bit more of a background, a little bit something you can kind of go through more on a step-by-step basis if you need to. But rest assured, you don't necessarily need to know all the steps. You won't have to write any of these transformations for yourself in here. Okay. But matrix multiplication in and of itself is every game engine's best friend, especially as you get into 3 dimensions. This is a 2-dimensional, even though it's a 3x3 transformation matrix, this is for 2-dimensional math here, right? This is when I want to say, okay, I have a position or I have a vector which has an x and a y, and I want to do things like translate it, rotate it, scale it, that sort of thing, right? Now, transformation, rotation, scaling. Okay, hopefully, or maybe these, it's a little light went off in your head. You might be remembering, you might suddenly recall that over in the Unity engine, we have this matrix up here, which has a position, a rotation, and a scale. Okay. So position, x, y, z, we have an absolute position, but then potentially we have a rotation and a scaling kind of going on. So what's happening here is this combination of vector and matrix, and this is sort of an intermediate form that Unity is having here. There are ways to, you don't have translation built into this matrix. You have rotation and scaling built into this. You could also, with this matrix, do things like translation, but we don't have translation because we just have a position here. But they're very related, which is why you should kind of know about them. Okay, so the type of things that are being accomplished by this rotation and this scaling are done through these transformation matrices. Right? So when you're paying attention in linear algebra and you said, when will I ever use this? Boom, here we are. We're using it. Okay. So for example, now these are referring to this matrix in the middle here, or M11 through M33, right? If we look at these common forms of a transformation matrix, certain common forms correspond to certain operations we would typically do on a position. So, for example, a translation, if we wanted to change the location of an object, we know its current position, and we want to move it to another position, right? We use its transformation. We use its, oh, I didn't want to do that. Wrong. I did the wrong back there. Sorry about that. Oh, that totally threw me off. All right, let's go back to that one. There we are. You'll notice you have x, y, and we have this bonus, this 1 over here. Right? So remember that there's a 1 in this value. Now, so the multiplication, x prime over here, okay, let's try to give you the digest version for those of you who aren't as familiar, right? The way we get x1 is we say x times m11, y times m12, and 1 times m13, right? So we're going to multiply this row by this column, and then this row, to get y, we're going to have this row, this column, and then w, which we're not going to use in this case, we would get that for w. So just disregard that. It's just important to have this to make it work, to balance that this is a balanced operation here. All right, so now think about in terms of that, right? If we have ones on the diagonal, and we have two numbers here, a translation in x and a translation in y, right? What's going to happen is that t1 or tx and ty, they're in our m13 and m23 positions here, they're going to get multiplied by 1 and just added into x and added into y. So that's why they translate, because they are just an addition, right? We're just moving that vector. We're using that vector to translate, to push our location to another location, right? So that's these two positions here, any matrix that has ones across the diagonal and zeros elsewhere, and just this is a pure translation matrix. Okay. This next one here is a pure scale matrix, where whatever these two numbers are, the x and the y, this would mean, okay, there is no translating value here. There is no, the y values do not contribute to the x values, so there's no rotation, right? It's purely a scale. It's just multiplying x by a certain value, multiplying y by a certain value, and that becomes our new one, because 0 and 0, nothing gets added to those, right? So this is what a scaling matrix looks like. This is what a translating matrix. And finally, rotation around the origin, right? So if you want to rotate around the origin by a specific angle, we just plug in the numbers here, and that's going to multiply everything. Now, rotation's a little bit funky, and we also start to talk about things like quaternions and how to make sure that, but for now, rest assured this is under the covers, and we'll talk about it in the exceptions of how this works. But a lot of the time we'll be able to just specifically say, give us a rotation around the x, or around the y, around the z axis for that particular object. This is going to be a little bit tricky, right? You'll notice here we had an x, y, and z rotation, and here we have just a single rotation, a single theta. Or excuse me, yes, right? Isn't that theta? Reason being, remember this is worth remembering. In a 2D game, there is only one rotation that can be performed, right? imagine you have your mouse on your desk. Your mouse can move X, your mouse can move Y. But the only rotation your mouse can make without it leaving the surface is it can only rotate around its center, which is it rotating on that y-axis, that axis that points out of, excuse me, the z, what am I saying, the z-axis, the one that points out of your desktop, right? So in a 2D game, we only have one sort of meaningful axis of rotation, which is our z. So remember that. That's why often we'll see manipulations that are we just refer to rotate when we rotate 2D objects. We don't say rotate in what around what axis. We say rotate. Kind of cool. There's also special versions, or commonly things known as skew and shear, where you kind of shift things and collapse things with regards to certain types of matrices. But we won't really discuss those. Leave those for more advanced topics. So those are sort of the main math. We're covering, linear algebra, the entire class of linear algebra in like 3 slides in here. So that's what I'm saying. Don't worry. Don't have to get too carried away. It's just more important to know about the concepts. And if you try to do fancy things where you are trying to really manipulate objects, you should be aware of potentially what's going on in there. All right. Let me grow my screen just a little bit to try to increase the font. I'm not going to worry about going back into full screen mode here. All right. So there are a few other matrix and vector operations that are worth worrying about. Well, vector operations specifically, because these will come in handy, especially as we start talking about AI, which is going to sound odd. It's not really true AI. It's more the things we do in games that allow us to make sort of algorithmic decisions about relationships between things and make things appear to have some sense of intelligence. Like, oh, is one thing looking at another thing? Are they facing the same direction? How are they, what is it, what kind of decisions, what kind of judgment can it make about a particular relationship of objects? Okay. And we'll sometimes use some of these quote-unquote fancy comparative vectors or vector comparisons to do that. And I'm sure you've probably heard of these before. Dot product. Dot product is one of the main ones. So the dot product of 2 vectors is defined as where we multiply each component of that vector and we take a summation. We get the dot product. Okay. Again, I'm not going to ask you to implement that. Not going to worry about that. Don't worry. Okay. So rather than so this is not the product of magnitude of each vector multiplied by cosine. That's not right. So what we can use this for, which it's always, to me, it seems like an odd thing outside of this, but in game use, we can use the normalized version of vectors. If we have 2 vectors, we take their normalized versions, so they're pure directional vectors, and we take the dot product between the two. An interesting thing happens, right? If we have 2 vectors, we have 2 directions, and we take the dot product, if the vectors are in similar directions, meaning they both imagine they were both either left-facing, right-facing, sort of thing, up-facing, down-facing. So they kind of generally face in the same direction. The dot product will be positive from 0 to 1. If they point in sort of opposite directions, so you have a left-facing and a right-facing and an up-facing and a down-facing, that sort of thing, those are generally going to be to indicate that they are in opposite directions. They have to be 0 to -1. So the nice thing, we do have this built in. Vector 3, vector 2, dot. We give those 2 vectors, and we'll get this nice scalar back, and we can use that scalar to make some cool decisions. Like, okay, does the enemy see the player? Right? So is the enemy facing in the direction of the player? That also involves, we need to know that the direction, not just the location of the enemy, but the direction in which the player or the enemy is facing. Okay, we'll get more into that as it happens, and it'll really become more of a thing in Project 3. All right. And if you're interested, you can go to the lecture notes and you can kind of check this out. There's a very interesting simulator for this. Let's see, can I follow this? Open link? Yeah, we'll give that a try. All right, maybe it went away. Maybe I don't have, maybe I didn't copy the whole thing. Oh, maybe not. Maybe it went away in the meantime. Oh, well, it used to be a really cool simulator. Sorry about that. That would actually let you do things like, create two vectors and give you the instantaneously what the dot product is and so on. Let's see. Nope, it's not there anymore. No, that's bad. All right, I need to find a new one. Okay, so that's math. Hopefully, you can refer back to that. If you want to crack open your linear algebra book, by all means do that. If you want to look for more reference on linear algebra, by all means do that. This is the double-edged sword of not having a required textbook in this class, is that if you do want to go out on your own and learn some more of that topic, you will have to do a fair amount of searching on your own, perhaps. But I didn't make you buy a textbook. Anyway, so that's the math. Be aware of the concepts. Some of them we'll come back to as we go on. But in the meantime, now that we know about this math, let's talk about physics, right? And we're going to talk about physics in a bit more of an abstract way. We're not going to necessarily get into force equals mass times acceleration and so on, maybe eventually. But for now, let's just talk about the type of physics that we're interested in, especially as it comes into the next game. All right. So in our case, we're going to be talking mostly about dynamic systems. I'll get into what that means. And we're going to be talking about rigid body physics. So we're going to be talking about some very specific branches of physics. So dynamics is most easily and most often defined in terms of a closely related field, which is kinematics. And inside of the Unity engine, occasionally you will be given a choice to say, do I want this to be a dynamic or kinematic rigid body? How do you want this thing to behave? And what that means is kinematics is the study of movement over time, but it doesn't concern itself with what causes the movement or how things get to where they are in the first place. It just deals with the movement itself. But dynamics, on the other hand, is the study of forces and masses that cause the kinematic quantities to change as time progresses. So dynamics are going to be more useful for us. Okay, we're going to be able to exert forces. We're going to have objects that have masses and are susceptible to gravity and force and all that sort of thing. So generally, when we want to have simulations, when we want to have things that act as if they were acting in the real world, we're going to use dynamic physics, dynamic rigid bodies to do that. Okay. So to do that, what tools does Unity provide to get you there? Thankfully, a lot. There's a lot of tools in there. And we can definitely fill a whole nother lecture with each and every one of them. But to get you started, the main ones we want to talk about, and one of the primary ones, especially in 2D games, is first off this thing called the rigid body 2D, and that is what by putting that component on an object, that kind of enables physics for that object. So it will then suddenly fall in your scene, right? So let me jump over to my example over here, and this is directly the last video that I did before this has this one in here. So in here I'm going to hit play, and this scene you'll see, hopefully, I've got my destroy apples button, but there's going to be a whole bunch of apples here, and they all fall to the bottom of the scene, right? So I have this red apple, and I'm going to do this. I'm going to just put this red apple, let's see, I'll go to the scene builder. Let me go to the scene builder, make this a little bit easier in case you haven't already seen that. I'm just going to say return there. Let's see, will it be okay with that? It's got unreachable code, but that's what I want it to do. All right, so it's playing, and nothing's happening because it doesn't initialize any apples. So I'm going to take this, and I've created a prefab. And this is apple tree prefab of this apple. Okay, and let's go into our scene. Go by our camera. Where's our camera here? Main camera. Interesting. Here's our canvas. Here's our main camera. There we go. All right, here's our main camera. So let's drop this red apple into the scene here and hit play. and you'll see this apple drops. It falls from top to bottom. Why does it do that? Well, because it has this rigid body 2D attached to it. Okay, it has this rigid body 2D component, right? So if I had just a sprite, say I had another, I'll go to my sprites here, and I have a green apple. My green apple is just another image. I happen to be a big fan of Lego. So I have some transparencies. Here's an apple. Now it's created a sprite, another sprite in my scene. So we have this green apple. And if I hit play, you'll see that the green apple is not going to fall, whereas the red apple does fall. Right? Because the red apple has that rigid body 2D on it. If I want to make the green apple fall, I always can say, okay, add component rigid body 2D. And by default, it's going to say, okay, it's dynamic. It has a mass of 1. It has a gravity scale of 1, and so on, so that it will fall down. It has no constraints on it. Constraints allow you to freeze it in certain dimensions. You'll see, okay, look at this. First clue, freeze rotation. We can only rotate in Z. Right? So we can freeze its position. We can freeze its rotation if we wanted to. All sorts of ways to manipulate that rigid body. But the default state for it is just going to be, okay, boom, we have gravity. All right. Now, one thing worth mentioning about gravity, okay, because this will come into play in future things as well, the game has, or the project is going to have a default value for gravity. And gravity, of course, has some sort of direction to it. In our case, we think of gravity as pointing down. So sometimes there's going to be things that you're going to want to go into your Unity project and change. So we're going to go to Edit, Project Settings, and introduce you to the Physics 2D settings. Okay, these are the things that generally govern the overall settings of the 2D engine here, right? You notice there is a physics setting for 3D. We're not going to worry about that just yet. But physics 2D. There's lots of other things, other settings for your project. But for now, let's just look at physics 2D. You'll see it is set gravity as being negative 9.81. Yes, this is in meters. So 1 is 1 meter, if you didn't know that in Unity. It is metric. And gravity points down in this case. Now, there may be other games where if we have a top-down game where gravity would not be pointing the y direction, we had no gravity at all. So we may want to change gravity or get rid of gravity in a game. Now, if we change gravity to 0 here, and we go over and play the game, you will notice that our apples no longer fall because they have no gravity. If I set that to a positive number, they are going to float up because it will say, gravity points in that direction. If I set it to a negative value, eventually, hopefully, they come back down. There we go. Shot right back past us. So their normal value is negative 9.81. Yeah, we'll kind of come back to that a little bit. So that's one of the most important things. You're not going to really need to change these other things for now, but we'll realize that's where they are, and eventually we'll start talking about this layer collision matrix. So remember that's where that is with their physics 2D settings. All right. So we've introduced now the simple, wonderful rigid body 2D. Now let's jump back over to our vectors and physics again for a moment. All right. So what physics tools does Unity provide? First and foremost, this rigid body 2D. Now, in and of themselves, rigid bodies cannot interact with other rigid bodies, which is kind of too bad. Well, no, it's not too bad. There are ways to control that, and that's through the use of colliders. So gravity, mass, drag, interaction, collision detection, all that. Unity is going to handle that through the use of these two things together. There's rigid bodies and colliders. And there's going to be a whole bunch of different types of colliders, mostly different shapes. Right, so you might have a circle collider, you might have a box collider, you have polygon colliders, edge, all sorts of things that you can define different types of collisions. And then there's another physics tool called a joint, which controls interaction between objects, the relationship with them, things like springs and hinges and slides and so on. We're going to worry about that a little bit later as well. So for now, we're going to start by looking at rigid bodies and also collider 2Ds. Okay, so what is a collider 2D? Where does that get you? All right, try to make this real simple. For now, I'm going to add another object to my scene. This thing here, this chest that in the game will be the thing I'll use to catch apples. And in order to make life interesting, I'm going to put a component on that, and it's going to be a box collider 2D. Okay, so there's a box collider 2D on there. If I hit play, still nothing is really going to happen. Everything falls right past because the apples do not have box colliders or any sort of collider on them. Okay, so you need this combination of colliders. So here, if we go ahead and say, okay, there's maybe a circle collider 2D on that apple, and we can see the shape of that collider. If I hit play now, aha, that object hit that other collider and stopped moving. All right. If I'd put a rigid body on this one, it would have been kind of odd because then this would have fallen down, and I might not have wanted that. So the rule of thumb is that objects that interact, both of them should have colliders, and at least one of them should have a rigid body, so that so that there is a simulation going on, right? Without a rigid body, generally there's no physics being simulated for an object and how it interacts with another object. So it is this combination of a rigid body and collider with another object that has a collider on it. Right? The simplest way to do that. Right? Lots and lots of fun that way. So we come to this one, we'll add a component, add a circle collider to that one, hit play, it hits as well. Now, a cool thing, if I decide to come over here, and you'll see I can push one object with another because these objects both now have colliders on them. And if I move them around in the scene, or I move them around in the scene screen, and I'll grab this game, we'll put the game over there, I guess. You can see the game being simulated and mess around with the scene designer at the same time. So we'll push that there, and now I'll push that apple. Eventually get it to leave this edge and fall down. And you'll see it even starts to rotate based on kind of how it interacts with that edge there. Right? So physics is quite powerful. There we go, back to here. All right. So what are the advantages of having a physics engine? Let's talk. You might immediately, you're going like, physics engine, fantastic. This is going to solve all my problems. I'm going to just make everything a physical simulation, and away we go. Almost. Slow down just a little bit. Okay. So having a physics engine is really great. And why is it great? Well, suddenly we don't have to script all the behavior. Right? I didn't have to tell the apple how to fall. I just said, okay, apple, you're subject to physics. So I can just create apples and any number of apples, and they will all fall. If you followed my other video, you saw a dozen apples, 16, 17 apples. They all just fell. Boom, wonderful. Okay, so it becomes easier. You don't have to script all that behavior. However, it does become difficult because of that. If you want to script behavior, then it becomes interesting because now you're going to have this clash of, basically our behavior in the real world is our fight against physics. Getting up in the morning is a fight against physics, right? You force your body to move up. You just don't naturally just get up. You just lie there. You just want to stay in bed, right? So scripting and physics are kind of the same thing. So scripting is the intelligence to your game, and it's going to be in constant sort of clash with physics to kind of resolve the two. And that's the way it should be. It works out great. That's why games are so cool. But it can make things challenging, right? So the moment you make everything a physical simulation, well, then your designer doesn't really have much in the way of control. You don't have much purpose to things. Everything just happens. It's just a simulation. It's not a game. Okay. But physics it's great because you have this wonderful notion of realism and world consistency because objects act consistently. All apples fall with the same gravity. You can make objects be certain sizes and certain masses and so on, and they will act as the typical user because the typical user has this wonderful reference point of the real world where physics works consistently. So they'll be able to understand it, right? Objects are going to do the right thing. It's kind of cool. However, that all depends on how good your model is, how good you've built it, how well you've set the parameters, and maybe it's not what you really want anyway. A pure physical simulation is tricky, right? If you want a car to behave exactly like a car, well, you can't just design. Then you have to figure, okay, well, where is the engine located in the car, and how heavy is this, and how you'd have to like really get into designing every minute detail if you wanted a car to really act like a car in the real world, strictly based on physics. So you might want to do things that really sort of violate physics and just sort of like script the behavior and have the whole thing move in certain ways, especially if you don't want to actually even design an engine, a motor for the car and so on. So sometimes it is tricky. It is really cool. We have this thing also potentially called emergent behavior. What is emergent behavior? Well, interactions that you didn't necessarily script but just sort of happen. Imagine a pinball machine. You don't think of every interaction in a pinball machine ahead of time. Or games where, hey, all of these creatures can wind up in the same little spot on the screen because they were all attracted to a certain thing, right? You don't have to think about all of these things ahead of time. They can sort of just naturally emerge, right? These behaviors emerge based on the situation in the simulation, which is cool. It can often be very surprising, pleasant, and and etc. But it also can be annoying because all of these things have no common sense and they'll just do what they need to. Everything will fall to the bottom. Everything will work its way through the cracks, and so on and so on. So you have to be very, very careful. Your game design may very well need to allow for unpredictable outcomes. If the player blows up the room and suddenly you had no constraints and the player destroyed all the entrances and can no longer get out of the room because it was a pure physics simulation, well, that's a bummer for that player because they're never getting out because you didn't design the fact that, okay, this area over here, you can't quite destroy that one because we need you to have that area to get out of the room. Things like that, right? So it's this balance of enforcing physics and violating physics. So it's nice. Players can exercise lots of creativity and control in the game, like having these free range open world sort of things. They can interact with anything and so on. They're really cool. It's great for world building and storytelling because you can kind of focus on those aspects of it without getting down into the nitty gritty of deciding, okay, how does every brick in the wall work, sort of thing. So it's great. There's lots of advantages to that physics engine, but you do need to have that extra level of control, and especially when you have creatures in the world, because creatures don't necessarily work in purely physical ways. They are making decisions. Like I said, they are sort of fighting against physics through their own free will. Free will is not a physical, it's not a physical property. Otherwise, I'd never get out of bed in the morning. Like I said, I would just, we'd all be sitting, certainly never get out of our chair or walk across the room. We're kind of moving against the tendencies of physics. So we have to think about how that's going to factor into our game. All right. So that's my spiel on physics for now. Keep those things in mind. All right. Now, the next game, our next project, is this thing called Apple Picker or Kaboom. It's based on this Atari game from a long, long time ago, but we often refer to it as the Apple Picker game rather than the Kaboom game. I don't know, I guess for copyright reasons. So David Crane wrote this game for the Atari 2600 back in the day, a cartridge, working for Activision. It's a really, fun game. And the idea is that you have this sort of mad bomber that basically moves back and forth on the top of the screen, and the mad bomber drops these bombs at some rate. And the rate increases. It starts off maybe one per second. It gets faster and faster and faster as the things move on. You also see that the bomber up at the top of the screen is moving randomly, it's not just moving completely side to side. Certainly it changes direction when it hits a side, but it also randomly changes direction all the while, as if it had some sort of control over itself. It's not just moving according to physics. It has some sense of, purpose here, right? Now the bombs, they're dropped according to physics, right? At any particular moment, I mean, they don't have any left to right physics, so they don't have they're not dropped with an arc, I suppose, in that, or whatever. But once the bomber here, once our bomber drops something, then it's on its own. It has this behavior of falling down, right? So we are mixing some very simple physics in the game. We have the bomber moving left and right. We have physics moving these bombs to the bottom. Okay, so this is sort of the game we're basing things on. There's a score that's based on catching the bombs before they leave the screen. Okay, and if bombs get past the player, see the player has these sort of two, I don't think you can pause it here, these two baskets currently. And if the bombs were to get past the player loses one of those baskets, right? And if the player gets a sufficient score, the player may gain another basket, right? So the player is controlling this left and right. We're going to control it left and right using our mouse. But the general gameplay is going to be the same. Okay, we have an antagonist. We have our enemy up here, this bomber. In our case, it's usually a tree, and the tree somehow moves left to right, and it has certain speed. It's going to we're gonna mix it up with the types of motion that we do, in terms of being physically bounded by colliders or just it deciding, right, when to move. So that basically this guy up here is deciding to move in left and right. He's not colliding with the edge of the screen. He's just deciding to change directions once he reaches a certain point, right? So he's not subject to collisions. Whereas the interaction between the bomb and the basket, that's a purely physical interaction. So we can use a collision for that, right? So think about these different terms. All right, so we're going to come in there. So what we're going to need in our game, we're going to have a tree sprite, right? We're going to think about this two-dimensionally. You could use 3D objects if you want. If you have the Developing in Unity book, Jeremy Gibson in there actually uses 3D objects, very, very, very simple blob sort of things for the objects. I recommend you use sprites because they tend to look a little bit more fun. You can get a little bit more interesting, creative with it. I've seen versions of this game. It doesn't have to be trees. It doesn't have to be apples. I've seen people, storks dropping babies, and funniest one, boogers coming out of noses, and all sorts of things. Use your imagination. You can use whatever graphics you like. But the general idea has to be this mechanic of where there's an antagonist. So there's this enemy at the top of the screen that's going to move left and right and be controlled by a script. Not subject to physics, but controlled by a script. We're going to script that antagonist's motion. There's going to be apples. They're going to be the dropped items. The dropped items, once they are dropped by the antagonist, they are subject to physics. Okay. We have baskets, which are the thing that the player will control, and also they're going to be the indicator of the number of lives the player has left. There's not going to be a life counter on the side of the screen. There is specifically a number of baskets. You're going to start off with, say, 3. That's the general rule. Start off with 3 baskets, and you're going to lose a basket every time a apple or whatever dropped projectile, you miss it. Okay. There's going to be high score text on the screen. We're also going to have high scoring, right? So you're going to have your score and your high score, and that's going to be persistent. This is going to be cool. You can come back to the game and see how well you did. And the objects are going to have sounds, right? So you're going to have behaviors, like a apple splats against the ground. You want to hear the splat. If the basket catches an apple, you want to hear that noise of the basket hitting the apple. The apple being created or being dropped by the enemy, there should be a sound that the apple jumped out of the enemy's hand. Whoop, whatever. We do things like that. All right. So these are going to be the main objects in the scene. These tree sprites, apple sprites. These two here are going to be with prefabs. You're going to want to use prefabs for those. Now, in one case, apples, you don't know how many apples there are going to be. at any particular point in time. So this, we're going to maintain a collection of apples using our lists. The baskets, we could say, okay, we know there's going to be at most 3, at most 5. So this is going to be a very different kind of scale or scope. So this, we will use an array as our collection of baskets. So we'll have a list of apples, an array of baskets, a single enemy. Okay, so these are the objects you're going to see. There will very likely be some invisible objects, at least one invisible object. And so here, sort of our game components here now, we have our apple tree, our enemy, our basket, our apple. And in here, you see we have the manager. The manager is sort of the player, right? You could say, well, the player has control over things. The player has the score. The player kind of really runs things, right? Now, again, also in the book, the basket is sort of the thing that moves around. Now, I like to stress this, and I'll go into it in the details, that I think all games should have a player. It seems like an obvious thing. Baskets aren't really independent things. They don't live on their own. Now we'll start talking about the idea of really designing with these components in mind. You have some design decisions to make. Okay, so an apple has a sprite renderer, it has a Collider 2D, it has a rigid body, and it probably has a script, some kind of class that you're going to use for that apple to figure out, if it goes off the screen, that's something that only the apple knows about. The apple knows about its position in the world. So if a decision has to be made about that apple's position, it may have to use its own script to figure that out, right? We have objects that have independent things to them, right? A basket is going to have a sprite renderer and a collider, and it may have a custom script to move according to the mouse cursor, destroy the colliding apple, and set code, and so on. I think I recommend that we think about this player or manager as being a player is the thing that really holds multiple baskets. So the movement is not 3 baskets moving independently, but 3 baskets moving because they belong to the player, right? And I'm prepared to answer questions about that, and I'll put some examples as to why that is. So as we're going through these things, we are thinking about design questions like that, right? So then we also have on the screen on our canvas, we have the score text and high score text. That's obvious enough. All right. So I want you to start thinking about, the assignment here. Take a little bit of breath, a little bit from the project. You earned it from the first project. And what I'd like you to do, though, is to start looking at the videos that I just posted about the use of prefabs and the general physics, general rigid bodies. I will go ahead and start posting more kind of detailed things. Consider each one of those independent videos that's not part of the lecture. Consider them to be sort of a lesson or exercise. They're really meant to be, demonstrate a certain technique so that you can kind of concentrate on that and hopefully replicate that, work that on your own, right? So consider each one of those to be an exercise. And in the long run, the goal is that the projects are going to draw from those exercises. If you don't actually do those exercises and think about them in context of the project, it's going to be more work at the end where you have to then just kind of implement everything. But if you've done the things and followed and done those exercises along the way, that's going to be the foundation for the project. Your life will be much, much easier if you follow along and try to implement the ideas, think about the ideas as you go. All right. So take a look at those, try to follow along with those. The other thing that we're going to do from now on as well, as part of the project, and I'm not sure exactly, I didn't put a due date on these, but we'll figure that out, is that I would like you to design each of these projects, right? Where are you going to say, okay, I'm going to go exactly according to the script. This one, obviously there's like some specific things I'm going to look to see, but you can decide what is the antagonist going to be, where are you going to get your graphics, what is it going to be, like think about what the behavior should be, and you have some room for creativity outside of, the required elements, and you'll have much more room for that in your other ones as well. And the nice thing will be that design document should become sort of also kind of a checklist for you to say, okay, here's what I have in the game, here's the things I need in the game, which parts have I done, which parts haven't I done yet, and so on. And we'll refer back to those as you're going through things. So that is a little bit more than an hour worth of talking in class. So I'm going to shut down the lecture video for the time being, and there's plenty of the other videos for you to go through, and I will keep kind of putting the other videos up as I have time to get them, and I will grade the projects of the weekend, get them back to you for Monday. So I'll stay tuned on the channel, prepare to answer any questions, unless anyone has any questions for the whole group. I will do this. If nobody's typing, if not, I will count down from 30 and then say, all right. Maybe I should say, okay, go ahead and react. Thumbs down if you don't have any questions on there, so I know that everyone is at least still tuned in. So I'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When I get 12 thumbs down, I'm going to say, okay, we're all good. All right. How's the pace of online summer going in general with everybody? Is everybody doing okay? That's let me know if you have anything, if there's anything I can do to kind of help out with that. There was a town hall meeting yesterday. The pace in this class is great. Okay, whew, that's good to know. It's good to know. I know sometimes I can talk too fast and I don't know exactly what's going on. Can't speak for cryptography though. Ah, okay, you're taking a cryptography class. Okay. Tough, real tough, laughing aloud. Okay. Too much work. That can be. Hopefully, it's not too much work in this class. The key to this class really is keep up with it. Okay. Do things along the way. If you do things along the way, it's getting those last minute questions answered that's tricky. And I will definitely be scaling back. You probably, for those of you who were paying attention yesterday, will notice that I was trying to be as responsive up until nearly the deadline, as responsive as possible. I am certainly going to expect people to be on their game ahead of time, and the last minute questions, that will ultimately be one of the things that I sort of have to take into account in terms of how well you did. So be proactive, do things bit by bit, add things to your program a little bit at a time, and hopefully we'll be good. All right, there was a town hall meeting. I don't know if everybody watched the town hall meeting to kind of hear what the fall is going to be like. It's going to be really weird. I think juniors are going to be on campus, but I'm not sure how the arch is. So, let's see, freshmen, seniors, and juniors will be on campus, is my understanding. We'll see how that goes for everybody. So poor sophomores are going to be kind of remote. All of my originally fall away friends were panicking. Yeah, I don't know exactly how that works. Side question: can we do an index? Let's see what this is. For you to look up the. I will try to do. Let's see, keywords. I'll try to put more keywords. Well, they're not going to really show up in the. I'll try to put more keywords in the titles. I'll try to be as descriptive as I can in the titles, even more so. I've been getting a little bit better on those, and specifically so you can tell which are the lectures, which are the project exercises, and I'll continue to kind of refine those more as well. I do appreciate your feedback on those. If you think, if you want to leave a comment on any of those videos or a thumbs up or anything like that to let me know, like, was this one too much? Do you want this more detail on that? Feel free to also comment on those videos, so that could be helpful to everyone as well. Yeah, it's tricky coordinating all of the resources at this point. I'm still trying to figure out what's going on with regards to LMS and the videos there. There's still some issues. I don't know if they haven't increased the amount of space I have, but I still am unable to post a lot more video. So we'll work on that one. So do all fall away juniors have to come back in the fall? Is that the Is that so? All juniors are coming back in the fall? Is that what you've heard? Yep. Hmm, that is interesting. All right. Um, as an advertisement, and this is unusual because normally I would not advertise this to my intro to game programming class, but we're going to be offering a new class um, called computer graphics. And you may have heard computer graphics before. I'm coordinating this with Professors Cutler and Professor Franklin. Um, and we are going to be offering for the first time a computer graphics course that is part of GSAS, because some of the other ones, some of the other courses, I guess the original computer graphics course isn't being offered through ECSE as much as it was, and it is. We are going to make it. There's going to be a certain number of slots. We're going to see how it goes, but there will definitely be a certain number of slots for non-GSAS students. Okay, at least 7 out of 20, I think was what we were thinking of doing. It's going to be, the goal is that it will be very much OpenGL and fundamental concepts and C++, so that we'll better prepare, and also we're going to be shifting a little bit of things. People who have been taking game architecture has been a tricky course. I haven't been satisfied with it. Some students, got a lot of feedback on it. In general, it's been a really crazy one thing to begin. So we're going to be kind of balancing out computer graphics and game architecture using this kind of new sequence of 2 courses. And we'll have a certain number of outside of GSAS slots in both of those as well. So keep an eye out for it. I don't know if you can register for it yet, but I'm gonna do my best to make it interesting. Here's the hint: if you look for my current interactive, is it Art for Interactive Media? If you look at that slot on um, on SIS, that's when it will be. It will be available this fall for the first time. So just be warned, it is going to be the first time. So first time courses always have some fun to it. All right. So keep an eye out for it. I'm going to stop the streaming at this point and stop recording because people aren't going to. All right.